you have to know that things like this start just from one thing, which is a dream. My dream was that all students could be able to develop projects in our university. Here we want to establish something which is way bigger. I would say a company, more or less. But for doing this, we need all of you.
Its wings one final time for the start of a sentimental journey into history.
Welcome everyone. I am Gianmarco, and today I'll be your host for this webinar. So later will join us Chiara. She will help me read all your questions for Giuseppe Cataldo. And a warm welcome to Giuseppe. It is a real honor for having you today for PoliSpace. So thank you. And Giuseppe Cataldo is the Chief Engineering of NASA EXCLAIM mission and the near-infrared camera NASA is contributing to the PRIME telescope, as well as the head of modeling and uncertainty quantification for backward planetary protection of the Mars sample return, capture, containment, and return system. So Giuseppe has contributed to a variety of NASA missions, project, and technology development programs, including instrumentation for space telescopes, payloads for Earth imaging satellites, and advanced concept for lunar exploration. From 2014 to 2020, he worked at the James Webb Space Telescope. So today he will do a presentation that will provide an overview of the Webb Space Telescope, which will succeed the Hubble Space Telescope in our quest for the first galaxy formed out of the darkness of the early universe. So thank you again, Giuseppe, and now you can start your presentation.
All right, great. Thank you very much, and good afternoon, everyone. It's a real pleasure to be here with all of you today, it's very to be here and to talk about the James Webb Telescope. We are only about 10 days from launch, so we are very excited and a little bit nervous at the same time. So, but here we are, getting closer and closer finally after many years of development. Today's presentation will provide a brief overview of the project, some of the challenges encountered, some of the innovations that we developed for such an amazing telescope. So I'll give a brief general introduction on the science goals, and then I will dive more into the engineering part of it. As an engineer, I contributed to all some of the engineering activities that we performed between 2014 and 2020. In particular, I did a lot of work on modeling and uncertainty quantification for Webb, and I was part of some of the test campaigns that we did at the NASA Goddard Space Flight Center, where I work. All right, so I'll go ahead and start the presentation. Feel free to let me know if something's unclear or if you don't see my screen at any time. All right, so I think you all should see my screen here, so I think the idea came many years ago. I think the Hubble Space Telescope has been in orbit for over 30 years now, and it's been a real workhorse for astronomy and astrophysics. Hubble has really revolutionized our science textbooks in many ways. But anyway, here I'm showing a picture of the Carina Nebula, one of many astronomical objects that Hubble has looked at. You can see this nebula is like the same name says, is a a cloud of dust, gas, as we would see it with our eye, okay, visible light. But the question is, what is hidden behind such clouds of dust and gas? So in order to do that, we need to shift to the infrared, okay, so to longer wavelengths, to be able to really peer through the gas and the dust and see what is hidden behind. Okay, so here we can see a number of stars and planets. So really nebulous are star-forming environments in our universe. Again, it's a picture that Hubble took. Well, both, in the visual and the infrared, but it's to say that, our eyes are incapable of looking at all the phenomena that happen in the universe, right? We need different eyes to look at different things, okay? So the infrared is one way of doing it. And today we'll talk a lot about the infrared because James Webb will be an infrared telescope. Okay, another amazing picture that Hubble gave us is the Hubble's ultra deep space field with about 10,000 galaxies here that we can see from the ultraviolet to the infrared. And it's a very, very tiny patch of the sky, and you can see how many things Hubble was able to detect. So it's really amazing, and it's very deep, which means that these objects are very, very old. So looking far in space is equivalent to looking back in time. I think you all understand this, right? So the light travels at a finite speed, and it takes time, right, to reach our planet, our eyes. So the further away an object is, in the sky, in the universe, the longer it takes the light to reach us. And so Hubble went very, very far in space and time, but not as far as James Webb will do. What we are really interested in is really to look at the history of our universe and go all the way back. So this kind of cartoon here shows a little bit the history of our universe in a snapshot. So we are on the far right of this picture here, the present day.
Sorry, Giuseppe, can I interrupt you?
Sure.
I think that you are not showing the slides correctly. We are just seeing the first slide. Okay, now yes.
Okay, so I was showing in full screen, so it looks like it doesn't work.
Yeah, it's okay like that.
Okay, then I'll do it like this. Okay, so
Okay.
now that means that you won't be able to see the animations, but all right, that's okay. I think we can deal with that. Okay, so this is the ultra deep space field that I was talking about with 10,000 galaxies from the UV to the IR. You can see Hubble right there. And then going to the history of the universe, snapshot. So we are on the far here on the right hand side of this picture, the present day. I want to go all the way back to look at when the first stars formed. Okay, so according to the current theory, so we claim that the first stars formed about 400 million years after the Big Bang. Okay, so that's the Big Bang, the very beginning of the universe. Then inflation, this is a very rapid expansion of the universe, and then we have what we call the Dark Ages. Okay, so there was no light, or at least the light and the matter were all entangled, and there were a lot of phenomena happening in those times. I'm not going into the details of those, but then we go again 400 million years after the Big Bang, and that's when the first stars formed. Okay, and then stars started to form, and they started to kind of get together in galaxies or more complex structures. Okay, and then planets start to form, and we see we witness really the formation of solar systems like ours, right? But it took many years, right, to see the universe the way we do nowadays. So Hubble got very close, but not as close as to be able to see the very first stars. Okay, so we need something like James Webb to do that. So we want to really go all the way back to detect this first start of what we call the first light. And then we want to understand the evolution of galaxies and stars and solar systems like ours. Okay, so and then we want to go one step further. So we want to really look at planets, exoplanets, so beyond our solar system, and understand really what they're made of by looking at really studying the chemical composition of their atmosphere. Okay, so these are the four scientific objectives that James Webb will try to accomplish. And so how are we going to do that? Well, in general, very briefly here, we have a plethora of telescopes on Earth, or I mean, really like on Earth or around our planet. So we have a bunch here on our planet, round telescopes, right, that usually detect the radio waves or visible light, right? That which is what the atmosphere is transparent to. Okay, but then there are other windows that where the atmosphere is not transparent to, so we need to go up, right? Either up in the atmosphere like Sophia, or with balloons, kind of spirit balloon, or sounding rockets, or even better, up in the beyond, outside the atmosphere, so in space. Okay, so we have a number of telescopes in space that look at different wavelengths, and so Hubble, like I said, is one of those in the visible, and we are gonna have James Webb join all these other space telescopes in the infrared. All right, so James Webb really will be the future of astrophysics in space. James Webb is an infrared telescope, like I said, will succeed the Hubble telescope, but it's really not correct to say that it will replace it. I mean, they are very different in nature, and will accomplish different goals. Okay, I like to say that they are more like complementary to each other, and we hope that they can work together for some time. But still, Hubble got very old and eventually will retire. So James Webb will be like the next workhorse for astrophysics. You all have heard that we are scheduled to launch no earlier than December 22nd. So we are getting there, and it's been an international collaboration of NASA and then the European, the Canadian Space Agency for many years. So you can see here a little bit of the main systems that James Webb is made of. So I will talk more in detail about each one of those over in the next few slides. But so you can see that it's got a primary mirror, which is what collects the light. The light gets bounced off the primary mirror to a secondary mirror here, and then goes into this black box called the apt optics, which includes a tertiary mirror, and then the light gets kind of travels, following some paths in this black box that we have here in the back, which is the integrated scientific instrument module, like a suite of 4 instruments that will allow us to analyze the light and look at produce images and data. Okay, so the upper part here, so the mirrors and the instruments, is what we call the observatory, so optical telescope element, which is separated by the sun shield through the core. The sun shield is a big shield, like the name says, that will protect the telescope from the radiation of the sun. And then at the bottom we have the spacecraft bus. You can say a little bit, the brain of the telescope, that will take care of all the controls. You can see the high gain antenna down here. It will allow us to talk to the telescope and collect data and send data back to it. There is a solar array, and then a momentum flap here for momentum control. All right, so who was James Webb? Why did we call the telescope after James Webb? So James Webb was the second director of NASA from 1961 to 1968. So he led NASA during the Apollo era. Well, really, all of it. There was Mercury, Gemini, and Apollo, and succeeded Keith Glennon, the first NASA administrator. He was not an engineer or scientist, but he really inspired NASA's scientific programs. And under his administration, something like 75 space science missions launched to study the as yet unknown environmental space. And we're really at the beginning, at dawn, right, of the exploration era back then. And he was a very good leader, and he made a lot of contributions. I mean, with him, really, NASA was able to make a lot of contributions to our discovery of the universe. So again, I think you're not gonna be able to see the animations here, so you'll see a little bit of an overlap here, but basically the slide was meant to show how James Webb compares to Hubble. So I'm gonna do this, okay? I'm gonna do it in a way that we can do it really quick. Okay, here we go. So you can see the primary mirror of Hubble, 3.5 meters in diameter, and a little bit taller than a human being, and then almost 3 times bigger than the one that James Webb had, 6.5 meters in diameter. Okay, which equates to approximately 25 meters squared collecting area. Okay, so much bigger, right? So bigger means more powerful, means that we can collect much more light, and that will allow us, James Webb, to look at things, also much better than Hubble at a given wavelength. Okay, so bigger and stronger, but here you can see a little bit to give you an idea of the dimensions of the telescope. So it's really big. It's the size of the sun shield is equivalent to the size of a tennis court. So 21 meters long, 14 meters wide, and approximately more than 10 meters tall. You start understanding a little bit the challenges of building something this big, and also the challenges related to how are we going to launch something this big on a rocket. But we'll talk more about it later. All right, so let's take a closer look at the mirror. The mirrors are really the eye of the telescope, right? It's nothing but an artificial eye that collects the light and then focuses it, okay, to the focal plane of the instrument, what we call the retina of our eye, right? But we'll talk about the retina in a few slides. So the mirror, really an engineering marvel, I like to say, that many engineers have come up with many years ago when I was still a little child, and the idea was to build a mirror that had to be big, but at the same time that it had to fit inside the fairing of a rocket. So the only way to do that was to do a mirror made of smaller segments that could fold. Okay, fold and therefore make the overall size smaller. So we could not do a monolithic mirror like Hubble, like I showed earlier, but a bigger one made of much smaller segments. So we got 18 segments that look like hexagons, right? All together here. Each of them has 6 degrees of freedom. So each segment can move in the 3 directions, X, Y, and Z, and can rotate around the 3 axes. And that's really because we don't want to have 18 different images of the same object in the sky, right? But we want those 18 segments to work together just like one bigger mirror. Okay, so there is a need to move them. Okay, make them move with with one another, and to be able to again make sure that the light again the images that we collect are just one and not 18. And then also each segment is able to change its radius of curvature. Okay, so basically we can change the shape of the mirror through some actuators that I will show on the next slide. Okay, the mirrors are made out of beryllium. So why beryllium? Beryllium has a lot of good properties for something like Webb. So it is 6 times stiffer than steel. It is 1.5 times lighter than aluminum. Many of you, I think, probably study aerospace engineering, Politecnico di Milano, you know aluminum, that's what most aircraft are made out of, right? So lightweight materials. So aluminum is very light, but beryllium is even lighter. So its density is 2/3 the density of the aluminum, so 1.5 times lighter. And so each segment only weighs 20 kilos. Okay, and then the third property is that beryllium is very stable from a thermal perspective. So I think like we can say that below 100 Kelvin, like it does not change shape anymore. So, I mean, like materials change shape if the temperature changes, so they usually tend to inflate as the temperature goes up, and they tend to shrink as the temperature goes down. So because James Webb will work at an average of below 50 Kelvin, so the materials are going to shrink, but again beryllium will be very stable at those temperatures. So very good material. But you may ask me, well, then why doesn't it look yellow? Well, it looks yellow because we added a very thin layer of gold to increase the reflectivity of the mirror. Okay, and then to protect the gold, we added a thin layer of amorphous silicon dioxide glass. Okay, that you can't really see. Very thin. Okay, I think like thinner than like human hair. So basically, like the amount of gold spread on the primary mirror is barely like 48 grams. Okay, so like just like the weight of a baseball, of a tennis ball or something like that. So only 48, I think, grams of gold. All right, so like I said, it will work at 40 Kelvin, more or less. So fun fact, well, I can say a few actually, but let's say if James Webb were on the surface of the Earth, look at the moon, and if a candle were lit on the shady side of the moon, the one that we cannot see from Earth, well, JWST would detect it. So okay, that's how powerful it is in terms of detecting infrared light. In terms of optical resolution, we can claim that James Webb would be able to look at the details of a coin, like a cent, from a distance of 40 kilometers. Okay, so that's how powerful it is. So we can see something like 100 times better than the human eye, and something like 10 to 100 times better than Hubble. Okay, so we really build a very powerful machine. So this is what the actuators look like in the back of the primary mirror. So you can see the structure of the mirror. The mirror was lightweighted, so we removed a lot of weight that was unnecessary. So the structure is really these ribs here that again make up the main structure of the mirror, and then you can see the actuators here that allow the each segment to like I said move and then correct the radius of curvature. Okay, well this is a model of course, but that's what it looks like. Okay, similar to it. Okay, well the mirror, like I said, focuses the light in the back of the telescope, the black box where the instruments are located. So there are 4. The instruments can be thought of as the retina, right? The rest of our eye. So that's where the light focuses on. Okay, and that's where the image is for. So there are 4. We have the here on the right we had the near-infrared spectrograph, which was made by the European Space Agency. That's one of the European contributions. We had the near-infrared camera here, and then we have the mid-infrared instrument, and then the fine guidance sensors here that will be part of the attitude control system of the telescope. I'm not gonna go into the details of each instrument. They are very, very complex and very difficult, but that's, the light will follow different paths inside, each instrument, and will get focused on the focal plane of the instrument. That, that's basically, again, where the images will form, and that's how we will collect data. With the spectrograph, right? Where the light will diffract, and we'll be able to look at all the different wavelengths and the chemical composition of the planet's atmosphere, as I said before. But I do want to talk about an innovation that we made for NearSpec. So NearSpec is very peculiar. It's because we'll be able to perform what we call multi-object spectroscopy. It means that we'll be able to look at up to 100 targets at the same time. Okay, so quite a change. Okay, from the state of the art, for space telescopes, be able to look at 100 objects at the same time, which means that we'll have an increase in scientific productivity also, that really, really big. So how do we do that? How can we look at 100 targets simultaneously? So we will do it through these little windows, little shutters, right, that open and close. Okay, so by opening and closing them in a certain way, we'll be able to basically, the light will be able to get through the open ones, and it will be blocked off, right, from the closed ones. So by doing that, we can target different objects in the sky and focus on those that we are interested in. All right, so these micro shutters are really, really, really tiny. As you can see, from this picture here to this one here to the one on the top left. So there are 4 quadrants, okay, and each quadrant is the size of a stamp. Okay, so imagine you have a stamp in your hand. Okay, that's how small one of those is. Okay, and in each quadrant, so in this very, in this postage stamp, imagine something like 62,000 windows like this. Okay, that's really how tiny it is, and you can imagine also the engineering challenges that came with building something like this. But again, it's only one of the many innovations that the James Webb will be bringing on board in the sky. Okay, now I want to focus on the sun shield. Okay, so it's a real thermal challenge. James Webb is a real thermal challenge because so the hot side will be at about 110 degrees Celsius, so 383 Kelvin, and but on the mirrors and the instruments are gonna work at 40 Kelvin, so minus 233 Celsius. So there is a big gap, okay, of over 300 degrees, okay, between the hot side and the cold side. So the challenge really is how do we make the temperature go down, okay, so much. So that's why we built a 5-layer sun shield, okay, that will separate basically the hot side from the cold side. Now the hot side is really hot, well, because of solar radiation, of course, but also because the spacecraft bus basically contains all the electronics, right? All the power systems, the high gain antennas, all the electronics, as generates a lot of heat, right? So that thing will generate a lot of heat that will not be good, will not help the telescope to cool down to 40 Kelvin, right? So we needed something that would allow this separation. So the sun shield will perform this job in a completely passive way. Okay, the only instrument that will be actively cooled will be MIRI, the mini-infrared instrument. It will be cooled to something like 6 Kelvin. Okay, that's the only instrument that will be actively cooled. All the others will be passive. Okay, so the sun shield will do the job to make the temperature go from 383 to 40 Kelvin. Okay, so this challenge is handled by, like I said, a 5-layer sun shield. So let's focus on the materials here on the right hand side. So each layer is 0.025 millimeters thick. Well, actually thin, right? That's very, very thin. So less than a millimeter. Each layer is made of captain. Captain is a very special material. A lot of good properties, including high heat resistance and stability. Then the layers are, so we added some aluminum, and the first 2 layers, we added aluminum and doped silicon. So aluminum, so why aluminum and doped silicon? Aluminum is highly reflective, so will basically reflect the light through the space that is between the layers. Okay, so we'll make the heat basically reflect off, in between the space here in between layers, and allowing the heat to escape. Okay, and then the silicon was added to because well, silicon is highly emissive. It's a good electrical conductor, and that's good because basically, for grounding purposes, we don't want the telescope to build up electrostatic charge. Okay, so these materials will do all these things, allowing the telescope to again reach the temperatures that are needed, and avoid all these other issues of grounding. So also the one main thing, okay, but why do we need 5 layers and not only 1? Well, because by adding more layers, we are basically, we also can use the vacuum between layers as an additional insulator. Okay, so that helps, again, the temperatures going down. Okay, go down from one layer to the other. The layer 1, layer 1 is the one at the bottom. It's relatively flat, whereas layer 5 here at the top is a little bit more curved. The layers are closer together at the center. Okay, so the distance between them is smaller at the center, and then it becomes larger toward the edges. Okay, so farther apart, and that's really because we want to direct the heat, okay, from the center of the telescope, okay, to the outside of the layers, okay, out in space. Remember what I said before, here at the center, that's where the spacecraft bus is, right? It generates a lot of heat, okay, beyond the one that the telescope will receive from the sun, right? So so the shape of the layers, and again, all the distance between them and so forth, all contribute to again direct the heat, okay, away from the observatory. Okay, the 5th layer is mostly for margin against imperfections from the other layers, and also to protect from micrometeoroid holes. Now you can see here actually these lines. These lines are real shields that prevent tearing from meteoroid hits. So imagine if a micrometeoroid hits the shield, the micrometeoroid will probably make a hole. Okay, and that hole can become bigger and bigger, right? So the tear can propagate right through the shield. But if you have something like this, like a shield like this, or multiple actually throughout the shield, okay, well the tear, okay, generated by the hole will stop right there. Okay, when you reach the shield will prevent, or will stop the propagation of the hole. Okay, so the hole will be limited in size. And won't propagate throughout the shield. Okay, so this is an extra protection that the sun shield has against these phenomena that may occur in space. All right, so moving on. JWST is going to live 1.5 million kilometers away from our planet. So for comparison, here you can see Hubble at about 570 kilometers above our heads, the Moon at 384,000 kilometers, and then Webb, okay, something like 3 times the distance that separates the Earth from the Moon. Okay, so why are we sending James Webb so far? Okay, so we are sending James Webb to the Lagrangian point number 2. So the solar Earth system. As you might know, there are 5 Lagrangian points for in this case the picture shows the ones for the sun and the earth and the moon system. So there are 5. So Lagrange discovered those many years ago mathematically, and there are really special points that we like to take advantage of for the many good properties that they have. So these properties basically are such that the gravity in this case of the sun and the earth basically mostly cancel out. Okay, so that means that we put an object here, that object will mostly stay there. Okay, and but then if the Earth moves around the sun, well, those points also rotate with the Earth around the sun. Okay, but an object will mostly stay there. Okay, but why did we choose L2? Okay, not L1 or the other. So, okay, for many reasons. So, if we were in L1, we would have the sun very closer to us. Okay, like I said, James Webb needs to work at cryogenic temperatures. Okay, so we need to stay as far away from the sun as possible. Okay, so L1 is not an option. L3, I mean, it's far away, but then we would have the sun in between that would not allow any communication with our planet. Unless we put some relay satellites, but that adds complexity to the mission, and we don't need that. So L3 not good. We have L4 and L5. The problem there is really that these 4 points, L4 and L5, are equilibrium points that are stable. That means like being a little bit in a valley, right? So those points collect a lot of debris. Anything that ends up there will basically stay. Okay, and L2, like L1 and L3, is an unstable point of equilibrium. So that means that the opposite, right? Being like on the top of a mountain. Okay, so imagine to have like a ball on the top of a mountain. If if you kick the ball, the ball will just go down, the slope, and there's nothing that you can do to bring it back up. Yeah, I mean, unless you go down to the valley, you pick it up and you bring it back, right? So the same thing with orbital debris there. So orbital debris are not really gonna stay there too long because they will feel all the perturbations caused by the gravity of the Earth, the Moon, the Sun, and so so that's why we like it. So that it's mostly a clean orbit. Okay, that's good for James Webb because it minimizes the impact of orbital debris or micrometeoroids. Right there. Also, L2, like the 1.5 million kilometers, the distance will remain pretty much constant. So that means that our data rate will be maintained the same, right, with the same round antennas of the deep space network. And then the astronomical targets also will be visible for very long periods of time, once or twice a year, right? We are not going to have the moon or the earth or the sun in between. We're going to look away from the sun and the earth, to outer space, and so we will really look at the sky, very, very well. All right, so in order to get there, we need a rocket, and the rocket will be an Ariane 5 rocket supplied by ESA. So right now the telescope is in Kourou, in French Guiana, where the launch site is located. Why do we want to launch from there? Well, Kourou is very close to the equator, so that's where we can launch our satellites or telescopes with more momentum, right? The higher angular velocity of the Earth, and also because of the orbit inclination, James Webb will be basically put in a direct orbit to L2. Okay, so the orbit was designed in such a way that we reach orbit in 30 days. And so on. So you can see here how the telescope will be folded inside the rocket fairing. Okay, so like I mentioned before, you can see some of the segments here folded, the secondary mirror all the way here, the sun shield, right? So anyway, I will show a video later on that shows the full deployment of Webb once in orbit. All right, so now I'm gonna show a number of pictures that will show a little bit the construction of the telescope. So here we are at the NASA Goddard Space Flight Center near Washington, D.C., where I work. This picture shows the clean room at Goddard that was used to assemble the mirror. You can see some of the engineers and technicians inside, and one of the 18 segments here in black that's being held by a robotic arm. You can see the robotic arm in action as it places the segment on the structure, okay, that holds the telescope. You can see it bigger here. And then you can see all the 18 segments, okay, on the main structure, okay. They look black because they were covered, right? They were covered mostly in order to being held by the robotic arm, and also to protect the real telescope from contamination. Possible problems, right, that might have happened during the assembly. But here it is, the primary mirror all assembled. Here we are in 2016, okay, 5 years ago. And you can see here a picture of the whole clean room at Goddard. Like I said, just a little anecdote here. You can see this window here on the right. That window would allow us to look inside the clean room, and so every time I would stop working every day, I had to stop by this window here to see what was going on in the clean room, and so I kind of saw this kind of really happening up under my eyes, and it was very, very, very exciting. Here we can see the engineers removing the covers, so you can see some of the segments coming out with the gold, and then here it is, the primary and the secondary mirror, in their beauty. Okay, so really, really nice. And well, I say, I'd like to say that I never really thought of ending up working on a project like this in my life. So here I am, when the telescope was brought up and kind of shown to all of us for some days. So we're allowed to take a lot of pictures in front of the telescope, and we're allowed to bring our families and friends here to show, really the many hours and days of work that we had put in. So, here I am with my boss before entering the clean room, during one of the test campaigns that we did here in the cryo vacuum chamber at Goddard. All right, well, moving on. After that, in 2016, we engaged in a testing campaign. So we did a vibroacoustic campaign where we simulated the launch environment. That the telescope would feel inside the rocket, and then we shook the telescope on this bench here to simulate all the frequencies that will build. This is still at Goddard. And then the time came to say goodbye to James Webb, destination Houston, where we said, hopefully we won't have any problems down there. So we were about to embark in another test campaign, very complex one, that was going to simulate the space environment, okay, in another cryovac chamber. Okay, so here you see the telescope was inside this white container that was put inside this military aircraft that flew from Maryland here down to Houston, Texas. Okay, and then you see the telescope about to enter into the cryovac chamber, the same that was used for the Apollo missions, okay, to simulate the space environment for the Apollo capsules. Okay, the chamber was refurbished for James Webb, but here it is inside the cryovac chamber. Okay, so this chamber is nothing but a big container, okay, where inside which we make vacuum, so we pump the air out, okay, to reduce the pressure. Like in space, there's no pressure out in space, and then we cool everything down, right, to simulate the cold environment of space. Okay, so that's what we did inside. You can see, some of the people there. You see how big this chamber is for comparison. So a lot of challenges in there. Trying to simulate the environment, to collect a lot of data, and then run the models at the same time. And that's really where most of my work was. So in all the models, the mathematical models that we put together to simulate the performance of the telescope in space. And the challenge was really here. You can see, we were only able to simulate this for the observatory, not the sun shield. The cryovac chamber, as big as it is, still not capable of keeping fitting the full sun shield in it. So in the end, we could never test the telescope in its fully assembled configuration here on Earth. Which is why we had to rely on mathematical models to really simulate the performance of the telescope in space. Okay, that's where most of my work really was devoted to. All right, so here we are then in California, Redondo Beach, in the Northrop Grumman facilities where the telescope was assembled. So put together with the sun shield. You can see here the different layers, one on top of the other. So final integration and testing for a couple more years, and then finally October 12th, like 2 months ago, it arrived in Kourou. The telescope was inside, was put on a barge from California, barge called M.N. Colibri. It was left California, went all the way through the Panama Canal, and made it to Kourou, French Guiana. So now there it is in the French Guiana, getting ready for launch. You might have heard in the news just a few days ago, we completed the fueling of the telescope. So we put all the fuel that James Webb will need on board. Okay, so before showing the video that will show the full sequence of launch and deployment, I want to say a few words about the application of James Webb. So maybe often people ask me, okay, but how much did it cost, and why so much money, and did we really need to spend so much money on something like that? Well, so the next 4 slides show briefly what do we do with all this technology, right? So is the technology that we develop for space just for science? But we say no. I mean, we really like to do a lot of things with it already here on Earth, all right? So what we call spin-offs. So some technology developed for Webb was used to improve actually the Hubble Space Telescope. So you can see some astronauts here, replacing some of the boards on Hubble, like some inter-array circuits. Okay, with the same that were developed for James Webb. Okay, so we can say that the investments made on James Webb allowed were used actually on a program that was well into the operation space, like Hubble. Okay. Not only that, the infrared sensors that we developed for Webb are now the universal choice for astronomical observations, both from space and around. And this technology is being used for Earth science, but also for national security missions. a commercial application. Okay, so the James Webb program has been a tremendous benefit to the creation of new technology and jobs beyond its direct funding. Okay, so for example, this company here, 4D Technology, went on to generate over $30 million in revenue from a wide range of applications within the astronomy, aerospace, semiconductor, and medical industries. Okay, based on the technology developed on Webb. So there's a lot of, but then I think probably even more important, medical. So a number of improvements in technology used for the measurements of the human eyes, we're now we're used to diagnose ocular diseases and potentially improve surgery. Okay, so for example, it enabled eye doctors to get much more detailed information about the human eye in a matter of seconds rather than hours. Okay, so it's just one of many applications that James Webb has already had on our planet. All right, so I'm going to quickly share a different window. Okay, so you should be able to see the video. Let me know if you don't, okay? So James Webb, like I said, will launch on Ariane 5. Here we are, 26 minutes after launch, we'll separate. The first thing coming out will be the solar array that will start generating power, okay, on its own for Webb. There will be 3 maneuver corrections on its way. Here we see, okay, the first one, I think. Okay, like I said, direct orbit injection to L2, and then we'll have the antenna deployment, so about 2 hours after the launch. It will allow us to communicate with Webb, okay? So beyond the moon, so beyond where every human being has ever been to, we'll see 3 days after launch the deployment of the forward sun shield pallet, and then the aft pallet coming down. All right, so it will be a very delicate sequence. Then will be the core, the tower will separate 2 meters from the spacecraft bus, okay, to provide the right thermal isolation. And then here you can see the different layers coming, being released and coming out. Okay, so the boom deployment will pull the layers out on the outside. And then each layer will start separating from one another. You can see the tensioning of the membrane and then the separation of the different layers. Okay, so it shows it very, very well. Then the momentum management flap deployment, and finally the deployment of the mirrors. Okay, so we are still at day number 6 here. So we'll see the cryo cooler will start cooling down the mirror, like I said before, and then the secondary mirror will come out. And that's the ISIM, the radiator panel, and then the wings. Okay, so it'll take 15 days to kind of deploy the full telescope. Okay, you can see here, and then we'll continue to cool down as it reaches the Lagrange point number 2 after about 29 days. Okay, then begin L2 halo orbit. Okay, it will be a halo orbit. Here it is, orbiting around the sun. All right, so I think that concludes my presentation. I will briefly reshare my screen simply because I want to say thank you to PoliSpace for the very kind invitation 10 days before launch. Thank you very much for all you did to organize the event. Very, very professional, everything. And again, now I'll be very happy to take any questions from the audience. And for any information, feel free to reach out to me and follow me on Twitter, Instagram, or LinkedIn. There will be a lot of media coverage happening in Italy. I will be in Italy for the launch. So the launch will be broadcast on Focus TV. So I will be there commenting the launch live. So feel free to join on December 22nd, starting at 12:45, I think, p.m. local time in Italy. And we are all very, very, very excited. So I'll stop, and I'll be happy to take questions. Thank you all.
Okay, thank you, Giuseppe, for
Thank you so
your
much.
presentation. Was really beautiful. Thank you. So now we will select a few questions. Chiara, you can start. You want to ask something? So
Yes,
go
I
ahead.
personally have a question for you. It's more on a personal level. I was wondering if working at NASA was your biggest dream since you were a child, or was it something unexpected?
Yeah, it always was my dream. As a child, I was, I think, only 8 years old when my dad gave me a book on the Apollo missions, and I was like, wow, that's really incredible. Somebody was able to land on the moon, and I always dreamed that someday I want to become an astronaut. But even just working for NASA was, always my dream. And yeah, the dream came true when I was 23 years old, and completely unexpected. That was unexpected for sure. I never thought that so young I would be able to join NASA, and and I've been there since. So I've been, I say, very, very lucky, and very, very, very happy to be there, to be able to work on many projects, something like James Webb.
Okay, thank you. And how did you end up working there? Was it hard from coming from a small town in Apulia to go and work in the US?
Yeah. So it all happened in 2009. I was doing a double degree in between Milan and France at the time, and I got this email from my university in France saying that there was a call through the European Space Agency for the NASA Academy program. It was a 10-week-long program that would host 20 students from the US, Europe, Japan, and Canada for like I said, 10 weeks to do research and visit all the NASA centers and meet with many Nobel Prize winners and directors of NASA, people like that. And so, long story short, I applied for the program. I was selected as one of the 2 European students for the program by ESA, and I flew to Washington for that in 2009. So I was here for 10 weeks, an exciting experience. And then the scientist I worked with at the time proposed me to come back to do my master's thesis with him. So I came back in 2009, and then after I came back, a month later, he offered me a job. So I was able to stay. No, it was not easy because, well, first of all, I mean, really all I did was to apply for the NASA Academy. So I always like to say, dream big, okay, never be afraid of putting yourself out there and try. Okay, try. If you don't try, you will never know the answer. So try. Don't be afraid. And then I think staying in NASA was not easy because there are a lot of restrictions if you are not a U.S. citizen. But we have a lot of good work and the support of good people like all my bosses. Was able to stay and overcome those difficulties. Again, it was not easy, but again, you need to be very strong, have a strong will. So with that, I think you can overcome a lot of obstacles, and so yeah, that's a little bit my story.
Thank you so much. It's very inspiring.
So there are a few questions from the chat. I'm gonna read it to you. So Gonzalo says that you mentioned due to its size, it was not possible to test the whole instrument in the vacuum chamber. So considering the issues experienced after Hubble's deployment, how confident you are the Webb will work as expected? I understand that like Hubble, there will be no option to reparation, right?
Yeah, correct. Yeah, no option for reparations. At least not, we haven't planned any. We are not going to repair it. Okay. If it ever happens, down the road in 5 or 10 years, who knows? But for now, we don't have any plans. So that is not one of the reasons why we have invested a lot of time, a lot of effort to test everything, okay, every system, okay, and then all the systems together multiple times, okay, over and over and over again, okay. That's also again why it took so long, because we cannot afford one single mistake, okay. Everything has to go flawlessly. No, you saw the video before. How many things need to go right? Well, the video really show all of them. There are hundreds of steps that had to go really, one after another flawlessly. Yeah, I mean, like I said, we always talk about 7 minutes of terror when we land on Mars. Here we're gonna talk about 30 days of anxiety, until we reach L2. So it will be really 30 days of, many things will have to go just right. Yeah, I mean, we've done all we can here on Earth to test everything, to verify that everything works well. I mean, true enough, I mean, you never know until you launch. So whatever will happen, during and after launch, it's really hard to tell. Again, there are many things that need to just go the right way, and but again, we will know for sure that we've done all we can, all we could, and that will be it. So there will be some critical moments. Of course, launch, the rocket. We don't want the rocket to blow up. So that's one thing, and then all the different deployments have to happen, all different mechanisms have to work. So, we pull the sun shield and all that. So will be really critical. As long as I mean, I think we can tolerate some level of damage or mistakes, but there are some that we cannot tolerate. So we'll see really what happens. But again, we did all our best and we will all the way through launch, to ensure that everything will go smoothly.
I think that with this answer, you already answered the next question.
Okay.
So let's move on. And Saba asks, is there any chance to get internship or some way we can join in NASA projects?
I mean, yeah, there are. The NASA Academy is really no longer an option. I think the program is no longer sponsored by ESA. Usually there are openings for postdocs. If you have a PhD, you can apply for the NASA postdoctoral program, which is open to foreign nationals as well. That's one option, and there are other internship programs, mostly through university collaborations that American universities usually have with NASA. So another way to maybe come study to the US and maybe find a way to get involved in some collaboration of that kind. There are a lot of restrictions in place for non-US students. So the entry is it's not easy, and there are ways or programs that each NASA center might have. Then NASA is really, when I talk about NASA, I mean I don't talk about JPL. Many of you may be familiar with JPL, and why do I make that distinction? Because JPL formally belongs to Caltech and has fewer restrictions than NASA. So JPL has its own internship program that you can. You all can take a look at, and there are openings there, and so I think there are more options there. But JPL, after all, works with us a lot, so they do a lot of cool stuff as well. So there are opportunities. Yes.
Thank you. So the next question is from Leonardo. So he thanks you for the beautiful presentation, and he asks, the choices of the hexagonal shape of the portion of the mirror is due to easy unfolding, or are other reasons for it?
Yeah, primarily that. I mean, we have to find a way to break the mirror in smaller parts, and so by doing the hexagonal shape that has a very high filling factor. Imagine if every axon were to be a circle, we would have gaps in between, right? Each circle, so we don't want that. So we want to have a surface that is as filled as possible. No, we don't want to have black holes in our images. So yeah, it's really primarily to the folding and then the maximization of the filling fraction of the mirror. I mean, yeah.
Okay, thank you. So there is another question from Andrea. So thank you, Giuseppe, of course. And regarding L2, it will be a popular destination for future probes mission from NASA or ESA, and how will this be handled? And it could be an issue for James Webb observation if there will be other probes over there.
Yeah, sure. Yeah. So if you saw at the very end of the video, James Webb will be orbiting around L2. Okay, so the halo orbit, it will be going around L2. It's an orbit that can be used by other satellites or telescopes. We do have other objects out there already, like WMAP is an example of a satellite. A probe, I should say, really. Out there in L2, there are others, and there will be others. But it's a very big orbit. The diameter, I mean, it's like bigger than the distance between the Earth and the Moon. So it's a very very wide orbit in the sense that it can fill a lot of we can put a lot of objects there. So no, I mean, then in terms of the observations, I mean, James Webb, I mean, there are a lot of room, to do all the observations that we want him to do, and like a very, very clear visibility of the sky, and again, all we need to be careful is the sun. James Webb cannot look at the sun. That's why the sun shield, needs to protect the telescope from the solar radiation primarily. Okay, so. So I think having our probes there, as long as they're well separated and they don't interfere with one another, I think we should be fine.
Yes, I wanted to ask you a question personally. What do you think? Do you think that James Webb Space Telescope will find traces of life in other exoplanets, or?
Sure, yeah. So I mentioned briefly before the fourth scientific goal will be to look at exoplanets and study their chemical composition more in detail. So I think that's what we want to do, look at planets in particular in the habitable zone of their stars. So that's already kind of, in a way, kind of restricts the options there, because we're trying to look at planets that that could potentially host liquid water. Right, so so yes, we are going to search for life with James Webb, at least life the way we mean it. All right, so with all the indicators that we think brought life here on Earth. As well as like liquid water, it's one of those, then there has to be the right, the right temperature, the right combination of things that that need to make a life possible on a planet. But yeah, I mean, I think the fields of exoplanets and astrobiology will benefit enormously from all the observations that James Webb will do. So.
Okay, thank you very much.
I think we have one more question. Can you briefly talk about on-flight characterization calibration mechanisms to reach the instrument performance requirements? Very long question.
Yeah, I mean, I'll keep it brief. It's really complicated, but I had a link on one of my slides that talks about the mirror alignment. So, like the actuators will work in a way that, for example, the mirrors will move with respect to one another. So that will take a long time. Okay, that's why it will take about 6 months for James Webb after launch to do what we call the commissioning, right? So we want to commission all the instruments, and we'll do all the mirror alignment, make sure that like I said, we want to look at just one picture of the same object, not 18 different images. So there will be that. So basically, the way we do it, we are gonna measure the wavefront error of the mirror and look at many things. I'm keeping it very brief here, simple. So based on the on that measure, we'll be able to adjust the mirrors by looking at the images and other optical features from merit to do that. Then in terms of again, like I said, the instruments will have to reach their optimal temperatures as well. So again, all of them will do it passively. So the cooling will start right away after launch, and then like the Miri will go down to 6 Kelvin with the cryo cooler that will do that. So that will start at some point during launch. You saw that in the video before. So we need also to calibrate all the temperatures. And we need to be the cold really because we are detecting infrared light, so we want to be above the infrared light that the telescope will emit itself, of course. So and then for all the things like attitude control, we have 6 reaction wheels, gyroscopes, star trackers, the fine guidance sensor that will all work together to make the telescope understand where in orbit it is and how fast it is moving, right, rotating. There will be some new maneuvers that will allow us to target, right, the stars and the galaxies, whatever we are interested in. So that's again done with the attitude control system that will work in a redundant way to acquire that information, right? So all the sensors do a course pointing at the beginning, right, and then we'll do the fine pointing, the fine guidance sensor, the other instrument that we have on board. Yeah, the interesting thing I want to say that everything will be really highly automated. So all the operations from Webb are fully automated. I think every operation cycle will last about 3 weeks. So for 3 weeks, James Webb will know what to do, okay? And if it ever encounters a problem with a measurement, it will just send a signal here on Earth saying, hey, I got a problem with this observation. You guys figure it out down on Earth. In the meantime, I'm going to escape and go to the next one. So it will keep moving. Okay. In the meantime, people down here will, understand, troubleshoot the problem, and then we'll re-upload on the next, operation cycle the new commands, and just will pick again that observation, go back to it, and do it. So we're not going to waste time, right? And that's what I said before. It will be very highly effective at producing, scientific data. Okay, so very, very, very cool.
Okay, thank you. We have another question, which is, what do you think is the most valuable teaching from the NASA Academy experience?
Yeah, oh my God, yeah, I learned a lot. I in particular, I think, I learned, to work in a high pressure environment, but in a team, to understand that really nobody expects you to be, a Nobel Prize winner at the age of 23, but rather how important it is to work together in a team, to learn from one another, and also because, the project we work on here in NASA really are always like pretty much at first, right? And nobody has done them before, so we all had to be creative and understand really how to tackle those challenges. So really teamwork is important, and be social, be very open to work together, and like I said, in a highly pressure environment, there's a lot of pressure here, a lot of deadlines, a lot of work to do, and but to understand that you need to perform that work really, really well. And again, you are never alone. You rely on your teammates, your colleagues, and even your boss, right, to do that. And I say this because I've had some very good bosses that were more than just a boss for me, were really mentors that taught me a lot of things, mentors that I could rely on every time I had a question, okay, without being fearful of asking, or oh, he's going to evaluate me. No, like, come and ask, okay. So and that's why how actually I learned so many things from them. So I think that's really one of the most valuable teachings I got during the academy. During the academy, I did a lot of leadership trainings as well. It was all about teamwork, like work together, come up with the ideas. And I think like the project, the missions that we're working on right now, if they become more and more complex, they require a lot of that. So.
Thank you. We have, I think, a last question from Andrea. He's asking about plans for a successor of the James Webb Space Telescope, and how does the future of Space Telescopes look like?
Sure, great, yeah. Great question. So I have a few backup slides. I don't know if I should show them. Maybe I will very quickly so I can answer the question with some visuals. Let's see if I can do it easily. Okay, so can you see my screen again?
Yes, I think.
Okay, so if you can, so one of them will be.
We can see that you want to share something, but we see only a blue screen.
Okay, interesting. All right, so I don't know.
I think now we.
Okay, sorry. Well, I'll try again. Sorry, I had stopped sharing. I got 3 slides that really answer this question very well, so I want to show them. Can you see it now?
No, yes, now I can see it. Yes.
Okay, great. So Roman, beyond JWST, the Roman Space Telescope is already under construction. I mean, will be much smaller than Webb, but it's actually a telescope that was given to NASA by another agency here in the government, and we refurbished it and redesigned in a way, to become, the Roman Space Telescope. So Roman will look at dark energy, exoplanets, infrared, astrophysics. The primary mirror will be pretty much like Hubble, 2.4 meters in diameter. It will also go to L2, halo orbit, where Webb is. Launched not earlier than 2025. So it will do a lot of high contrast imaging and spectroscopy of nearby exoplanets. Okay, we'll look at the inner Milky Way, so our galaxy, to find. We expect something like 2,600 exoplanets. So we'll do a lot of it, and it will do also what we call a survey. Okay, with this wide field instrument that will it's like 100 times larger than Hubble. Okay, so we can look at 100 times more than Hubble in the sky. So and then again, we want to look at the, like I said, dark energy, look at the matter as well, dark matter, how it's structured and distributed throughout the universe, and look at how the universe expanded over time. So that's coming up. But even beyond it, actually, we don't know really, but just like about a month ago, the results of the decadal survey came out that basically give recommendations of what to do, in the next decade. And so there were 4 big recommendations, or actually proposed missions. One of them was the LUVOIR. The LUVOIR is what we call the Large Ultraviolet Optical Infrared Surveyor. So you can see in the picture here, it's like a much bigger James Webb, right? Looks like a much bigger James Webb. The one I'm showing here is what we call Concept A, a 15-meter primary mirror. And Concept B was like 8-meter primary mirror. So to look at the cosmology, galaxies and stars and their evolution, comparative planetology in habitable worlds. So a lot of this new again, search for life and look for exoplanets. Again, it was one of 4 recommendations. There were 3 more. One was for an habitable exoplanets telescope. Another one was for an X-ray telescope. And then there was another one in the infrared and the Origins Space Telescope. Well, long story short, the decadal survey recommended something between LUVOIR and HABEX. So something more like, again, the size of James Webb, but focus on exoplanet search primarily. So again, it's a work in progress. People are going to start now thinking about it. They also recommended like a multi-year technology development program to actually develop the technologies for this next telescope, and they recommended a launch date no earlier than the 2040s. Okay, so we're really looking down, down the road, 20 years from now. So I think it's important to develop technology to improve, right? The instruments that we want to bring on board, and also if you're gonna bring build something like this, we are gonna start thinking about should we do it in space? Should we assemble this, in orbit already, and can we make the instruments serviceable, right? Like with the robots, can we take robots to the orbit of these telescopes and, for example, refuel, add fuel to the telescope to extend its mission lifetime, or can we do something with it with Hubble, right? Replace the instruments and to bring something better, right? Like the astronauts did with Hubble, and that's a primary concern because L2 is a very far distant orbit, and it's very difficult to send people on that far. So we need to start thinking about a robotic mission. So, but in general, yeah, I mean, slide really shows a little bit, where we are going. So Sophia, boys, 47, James Webb coming up, balloon missions 2022, Roman 2025, and maybe Lunar, or whatever the next will be in 2035 or 2040. It's really like they recommended a few weeks ago. So yeah, there's definitely a lot going on in this field, and we'll I say stay tuned, and maybe some of you may end up working on something like this. So.
Okay, thank you so much.
So hopefully some of the students at Polytechnical will work at this project one day.
I hope so, yeah.
So I think we are done with the questions. If you want to add anything, Giuseppe, please go ahead.
No, the only thing I would add is again a big thank you to all of you that have managed the organization of the event. I work with you a lot, Gianmarco. You are my main go-to person. So thank you in particular, but to all of you really for the kind invitation and for doing this for the people that are listening to us today. I know it's Sunday afternoon over there, so I told Gianmarco I couldn't really. It was the only thing I could be on my schedule, but I'm happy to do it, and I'm glad you take some time off, Sunday afternoon to join us. So
no, it was an honor for us having you, for all PoliSpace members. So thank you.
Thank you so much for your time. It was amazing.
Sure.
And a huge thank also to everyone who followed us today. So thank you.
Well, I'm glad
for listening. And I want to, this is our last webinar of the year, so I want to thank all the people that followed us this year, or the people that followed the PoliSpace agenda. And I want to suggest to everyone to subscribe to join PoliSpace, so they be updated on all the other events that we're gonna do next year's. Not only webinars, but we are planning to other events and surprises. So please, join us, and thank you again, Giuseppe, for joining us. Thank you.
Great.
It was a pleasure having you.
Thank you, Giuseppe.
Great. Thank you all. Bye.
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 You have to know that things like this start just from one thing, which is a dream. My dream was that all students could be able to develop projects in our university. Here we want to establish something which is way bigger. I would say a company, more or less. But for doing this, we need all of you.
Space shuttle spreads its wings one final time for the start of a sentimental journey into history.